using. And that is true because we all are dependent on fossil fuels. So there is a need in the technological forefronts that we need to explore some energy conversion technologies by which we can convert renewable energy sources into usable form of energy, be it electrical energy, or it could be a chemical energy, like a fuel, like hydrogen. So to highlight on these issues, we have with us Ms. Ankita. She's from IIT Hyderabad, from Department of Chemistry. So her research domain is basically on energy harvesting and photoelectrochromic devices. So Ankita, I welcome you for your talk.
Thank you, Anupama. A very good evening to one and all. As Anupama has already introduced, myself, Ankita. I'm a fourth-year PhD scholar in Department of Chemistry, IIT Hyderabad. I work on photoelectrochromic energy conversion devices under the supervision of Professor M. Deepa. Since this virtual talk series aims at advanced materials, I will try giving an idea on what kind of materials can be used in these photoelectrochromic devices. So firstly, I'll start with what are photoelectrochromic devices. Anupama, for some reason, I'm unable to move my screen.
You just start sharing your screen again. Like,
okay.
Click on stop sharing
maybe
and then reshare it.
Okay, I think that's fine. It's fine, right?
Yeah, it's fine. It's fine.
Okay. Okay. Photoelectrochromic device has emerged as an integration of a photovoltaic cell and an electrochromic device, which was first proposed by Bettinger et al. In 1996. Now, photoelectrochromic devices, or in short, we call it as PECDs, are self-powered devices which encompasses a dual behavior of energy harvesting and energy saving. Basically, it comprises of a photovoltaic function, that is, conversion of electromagnetic radiation into electrical energy, and an electrochromic function, that is, delivering a smart optical response on application of an electric stimulus. Now, these two functionalities require a proper gluing agent so that the device is complete. And for that, other than an electrolyte, also a transparent and conductive substrate and a proper circuitry are essentials. So I'll go into the details, but before that, I just wanted to show the pioneering work in 1996 was published in Nature Journal. This work is a DSSE-based PECD, wherein a ruthenium disensitized nanocrystalline TiO2 was used as the photoanode, WO3 electrochromic film as the counter electrode, and lithium iodine as an electrolyte. And they achieved greater than 20% transmittance change at 788 nanometer. These PCDs has a wide range of applications. They are used in sun smart glasses. They are used in window panes in aeroplanes. They are used in rear view mirrors in cars. And they are used as smart windows in solar shading in architectural glazing and skins of future building. Why so? Because there is a huge amount of energy conversion in heating, cooling, or lighting these residential buildings. But when you have an electrochromic material on the window pane, it provides a glare control as well as thermal and visual comfort management without impeding the visibility. So before going into the details of the working of PECD, I want to give a very brief overview of the two individual components of a photoelectrochromic device, that are the solar cells and the electrochromic device. I'm sure most of you are well versed with the functioning of a solar cell, but for the few others, I'll just quickly run through, so please bear with me. Solar cells. First photovoltaic module was built in Bell Laboratories in 1954. We all know the motivation behind solar cells is solar energy is a renewable energy source and alternate to fossil fuels. And till date, there has been 3 generations of solar cells. First generation is crystalline silicon wafer-based semiconductor. Now, this is the only PV technology that has been commercialized till date in spite of its expensive manufacturing cost. The second generation is the thin film deposit of semiconductor. And the third generation is the photoelectrochemical cells, which include DSSCs and quantum dot sensitized solar cells, QDSCs, on which I work on. I'm sure, I think what One of the speakers in this talk later on will be speaking about perovskite solar cells, which is the hot topic in today's world because it is another technology that will be taking a leap towards commercialization in the near future. Anyway, I will be speaking about quantum dot size solar cells. What are quantum dots? They are 2 to 10 nanometer sized luminescent semiconductor crystals that have unique chemical and physical properties. Due to their size and highly compact structure, basically they are the light harvesters in these kind of solar cells. Now, working principle. How do these solar cells work? Upon illumination, there is a photoexcitation that occurs in the quantum dot, leading to an exciton pair generation. An exciton pair is an electron and hole pair. The hole remains in the valence band while the electron gets transferred to the conduction band of the large band semiconductor, TiO2 or ZNO, whatever the case may be, in the photoanode. This causes charge separation. Now, this ultra-fast charge injection from the conduction band of the quantum dot to the conduction band of TiO2 or any other large bandgap semiconductor is followed by quick scavenging of the hole that is left behind in the valence band of the quantum dot by the by the reduced species of the redox couple, that is polysulfide, and then the electron that is there. Should I go a little slow?
Yes, Ankita.
Yes, Ankita.
Slow pace.
Okay. I thought, okay.
Yeah.
Sorry, I'll go a little slow. So
Yeah.
Oh, sure.
I'll start once over again. So when
You can
when
continue
this quantum
from
dots,
the point.
okay. So as I said, upon photoexcitation, there is an electron-hole pair generation. The electron marked in green in the conduction band of quantum dot, it gets transferred to the conduction band of the large bandgap semiconductor or the photoanode. Now from there, it moves to the conductive substrate and then starts flowing through the external circuit to reach to the counter electrode. Now, from the counter electrode, there are already, as I said, because of the quick scavenging of the hole from the quantum dot, there are oxidized and reduced species both present in the electrolyte. So these oxidized species, they capture the electron from the counter electrode and undergo reduction. So likewise, this sulfide electrolyte is regenerated and the entire cycle is completed. So the redox couple needs to undergo oxidation and reduction simultaneously. So when it is undergoing oxidation by taking the electron from the valence band of the quantum dot, it is also undergoing reduction at the surface of the counter electrode. Here I want to mention a term called Shockley-Queisser limit. Basically, this is the maximum theoretical efficiency that any solar cell can achieve. That is around 33.7 to 34% under AM 1.5 100 milliwatt per centimeter square sunlight. But we have reached nowhere close to this value because of several charge recombinations that takes place in these kind of cells. If you see the blue dotted line, they are the charge recombination pathways at different interfaces. So firstly, there can be an internal charge recombination that is between the electron and the hole inside the quantum dot. There can be a back electron transfer from the electron in the conduction band of the photoanode to the valence band in the quantum dot. Similarly, there can also be electron-hole recombination between the electrons in the conduction band of the photoanode and the oxidized species in the electrolyte. So there are oxidized species in the electrolyte which will have a tendency to take the electrons from the conduction band of the photoanode or from the conduction band of the quantum dot. So these are pathways which needs to be overcome if we are aiming at a high efficiency solar cell. Why QDSCs? Now there are definitely some advantages which has made people to move from a dye sensitized solar cell to a quantum dot solar cells. So these are discrete energy levels, tunability of light absorption, multiple
I request Sumannath to kindly mute yourself. Yeah, the echo sound is getting echoed. Please.
Please, may I continue?
Yes, Ankita, you can go ahead.
Yeah. So you have tunability of light absorption, you have multiple excitant generation. These QDSCs are pretty cost effective. They are very there are simplistic synthetic procedures, and they are sensitive to diffuse light. Now, what I mean by discrete energy levels is that in semiconductors, you have band structures, that is conduction band and valence band. When you move towards a molecule, you start getting discrete energy levels.
Hello.
Hello.
Hello. Wait, Ankita. Sumant, you
Okay.
want to say something? Okay, Sumant. Please put your mic on hold. Okay, Ankita.
So when we, because of the discrete energy levels, what happens is when you shine a light of a particular wavelength, say, so in the second figure, if you see 450 nanometer, depending on the size of the quantum dot, the emitted light has its particular color. So it is all dependent on the band gap. So if you have a 6 nanometer sized quantum dot, and if you shine blue light, the emitted light is in the red region. Whereas if you have a smaller quantum dot, that is 2 to 3 nanometer, you have it in the blue to green region. Basically, light absorption can be tuned depending on the size of the quantum dots. Now, what is multiple excitant generation? Hello?
Hello, Sumant. Do you want to say something? Hello.
Rishabh, you can mute everyone as a host. And then
Actually,
Ankita can unmute herself.
I
Yeah.
am muting everyone, but he's again unmuting.
Okay, no issues. By mistake, there could be because
Okay.
it's distracting a speaker. So,
Okay. Please, Sumant, please put yourself
Okay,
on
so
hold. Okay. Okay, Ankita, sorry for the disturbance. Please carry on.
no, it's okay. Am I audible now?
Yes, you are audible.
yes, Ankita, you can go. Yeah.
Yeah, okay. So multiple excitant generation. When the energy of a photon absorbed by a quantum dot is at least twice the band gap energy of the quantum dot, it can lead to the generation of more than one excitant pair instead of being wasted at heat. And others, I think it's pretty simple. So there are, like, if you want to go into the details of each of this point, I can explain later on. But I think most of you are well versed with these, so I'll move on. Deposition of an active layer of TiO2 can be done by two techniques, either Dr. Blade technique or a screen printing technique. And deposition of quantum dot methods can also be done by two techniques. That's the in situ methods and the ex situ methods. Now, in situ methods comprises of SILAR, successive ionic layer absorption and reaction, and chemical bath deposition. These kind of methods ensure good contact between the metal oxide scaffold and the metal chalcogenide because they are growing in situ over the layer of the metal oxide. Ex situ methods are like when you have already synthesized the quantum dots previously by a hot injection method or a hydrothermal method, and then you deposit them over the metal oxides, maybe TiO2, you do electrophoretic deposition, or you do simple drop casting or linker assistant deposition. Now for ex situ methods, there is a good control over the size and dimensions of the quantum dot as opposed to the in situ methods. Quantum dots can be of different types. They can be binary like CDS, CDSE. They can be ternary. They can be quaternary like cadmium, zinc, selenite, sulfur. There can be also alloyed quantum dots. There can be also core shell quantum dots of different types, type 1 and type 2, and so on. So this figure I've taken from this figure paper, Sustainable Energy and Fuels. This, not all, but quite a lot of quantum dots with their energy levels and band gaps. Also, there are few wide bandgap semiconductor which possibly can be used or has been used previously. I use TiO2, which has a bandgap of 3.2 electron volt. It's easily processable mesoporous form, but there are people who use ZNO or SNO2 as the case might be. Now, for the quantum dots case, I use CDS, which is a visible light harvesting quantum dots, 2.3 electron volt. There are also a variety of others which are listed. And there are different kinds of electrolytes. There are neutral electrolytes like ferroferry, there are acidic electrolytes, and there are alkaline electrolytes like the polysulfide. But a QDSC works best with alkali polysulfide electrolyte. This suitable redox couple electrolyte is necessary for the regeneration of the quantum dots. Now, there are various techniques to improve solar energy conversion. First, I'll talk about them in brief. First is co-sensitization. Suppose I'm using CDS, the visible light harvesting quantum dots, and I co-sensitize my film with PBS. Now, lead sulfide is a NIR light harvesting quantum dot. So together, we can have a broader utilization of the solar spectrum. You have a visible light, you have an NIR light, so there is broad spectral utilization. Secondly, we can have carbon materials or polymer addition. Now, these materials do not itself absorb light, but their energy alignment is such, and they're also highly conducting. So they escalate the charge propagation throughout the cell. Third, there can be plasmonic materials which show plasmonic enhancement or light scattering. Metal nanoparticles such as AU, AG, CU, these which has dimensions less than 50 show mostly plasmonic, and more than 50 maybe light scattering. The main work of these plasmonic material is that they enhance the absorption capability of the adjacent quantum dot. There are metal dopings. There are literatures on maybe example of Mn2+. When you have metal dopings, there are electronic states that gets created in the mid-gap region, and this ultimately lengthens the lifetime of the charge carriers. There are materials which shows fret. You can use different passivation layer like ZNS, SiO2, amorphous TiO2. When you have a passivation layer, you can overcome few recombination paths and therefore increase the solar energy conversion. Semiconductor morphology also plays an important role. If you have 1D structures like nanowires or nanorods, they are much better than nano sheets or nanospheres, which are 2D or 3D structure, as the case may be. Because in 1D structure, you have unidirectional charge flow. Similarly, quantum dots tethering also plays an important role. Last, not the least, that is suitable counter electrodes. You have to choose a proper counter electrode which aligns well with the other components of your solar cell. It has to be highly conducting. It has to be high surface area, high electrocatalytic activity. And finally, integration of a solar cell with supercapacitors, as we call photo supercapacitors, or electrochromic devices, as is my case, photoelectrochromic devices. These also improve solar energy conversion in the long run. Then coming to chromism. Color reversibility in a material, depending on an external stimulus, is called chromism. There can be 3 different types of chromism: thermochromism, photochromism, electrochromism, and also others like solvochromism and others. Thermochromism is heat-induced color change. When you have a coffee mug coated with a thermochromic metal oxide, example maybe VO2, that is vanadium dioxide, what happens is if you pour a hot liquid in that coffee mug, you see a color change. So the user from at a distance can identify whether that vessel contains a hot liquid or a cold. Similarly, photochromism, many of you have seen glasses which gets a slight exposed to tint when you're sunlight, which works as a sunglass, and then indoors the same glass works as our regular glasses, specs. They are light-induced color change. And in my case, we will be talking about electric potential-induced color change. It is reversible changing of color by accepting or donating electrons to cause electrochemical redox reaction. Photoelectrochromic device. This was discovered by S.K. Dev and J.A. Kuparian in 1968. And you see this figure, this work was done in our lab by one of my seniors. So electrochromic materials can be broadly classified into two categories. There can be anodically coloring materials, there can be cathodically coloring materials. Now, anodically coloring materials such as nickel oxide, which upon oxidation gets the brown black color, and this ferroferricyanide complex is the famous Prussian blue, which we get upon oxidation of the Fe2 cyanide minus complex, which was colorless, but upon oxidation, it gets the very famous Prussian blue. Cathodically coloring materials are certain transition metal oxides like tungsten oxide, molybdenum oxide, vanadium pentoxide. Now, these metal oxides, upon concurrent intercalation of a metal cation and an electron, undergoes reduction to form its respective bromes. These are called bromes. The lithium tungsten salt, these are called bromes. So what happens is, suppose in WO3, the W was in a +6 state, one of them gets reduced to the +5 state, which gives it the deep blue color. There are also conducting polymers such as P dot, Pani, Pro dot, which shows this electrochromism. Similarly, vialogens, these are diquaternized salts of 4,4-bipyridyl, also shows these kind of chromatic switching. Now, there are certain performance parameters of these electrochromic devices. First is low operating potential. Now, this oxidation and reduction reaction, this cycle has to operate in a low potential because we don't want to degrade the material completely. Now, if you see the plot on the right-hand side top, what you mean by high contrast ratio is when you take transmittance of a colored film, it is the red line. When you take the transmittance of the same plot in its bleached state, it is the brown line. So the difference is del T, that is the transmittance between the bleached and the colored state. This contrast ratio should be high enough so that it is perceivable by human eye. Large coloration efficiency is when this color change occurs with minimum charge intercalation. Fast switching kinetics and high cycle life. So I have been talking about previously of putting these materials on the skins of buildings. We cannot wait for hours for this color change to occur. So it has to have very fast switching kinetics, and it has to have very long cycle life because these windows or these kind of materials can't be changed on an everyday basis. Now, in my first slide, I've talked about a proper gluing agent. Why? Because the electrolyte needs to have certain characteristics to give a proper binding to this entire device. So this electrolyte needs to have an electrochemical stability window. It should be stable over a certain potential window. It should have good ionic conductivities. It should be thermally stable. And it should be transparent. If it is not transparent, then it will lose out on its utility as an electrochromic device. Finally, coming to photoelectrochromic devices. Now, since the report in 1996, dye-based PECDs have been investigated in details. Now, if you see, there has been reports on Pani, there has been reports on Pro dot. But if you see the last one, they have fabricated a micro-pattern bifunctional electrode of platinum and WO3. So that the main aim of this is so that you do not compromise with the solar cell efficiency and still be able to achieve a good transmittance modulation. That is greater than 30% in the visible region. In the initial reports, it was only 5.1%, but it went on to more than 30%. If it is very high, of 44% in the Pro dot Me2, you see the PCE is not very impressive. It's only about 0.2 or 1.1 in this range. So here we come to quantum dots sensitized PECDs. So the working principle of a quantum dot based PECD is very similar to a dye based PECD. What happens is upon photoexcitation in the anode side, electrons get generated and will move to the FTO glass, from which it starts flowing through the external circuit to reach the counter electrode. Now at the counter electrode, we have the electrochromic material, that is the WO3, coated over. So when this electron gets inserted into the matrix or the lattice of this WO3, so Na plus ions from the, or the cations from the electrolyte also gets inserted simultaneously. So then it gets reduced to form NaXMO3 or NaXWO3 as the case may be, and it gains the deep blue color. Now it is a reversible reaction, so under dark, the opposite starts to occur, or you can also apply a positive voltage to the electrochromic layer. So then what happens? The WO3 releases the Na plus ions into the electrolyte and also releases the sodium plus, also releases the electrons to get oxidized. And finally, this stage is again, you get the bleach state. This is the bleach state, whereas in the reduced form, it is the colored state. So how to design a stable low-cost quantum dot? So an ideal PECD, the device structure or the electrolyte should be such that the photovoltaic efficiency should be high. The electrochromic color contrast should also be high. The transition metal oxide, or the MO, as I've shown in the blue box here, should be stable in the redox couple RC, and the electrolyte, redox couple electrolyte, should also be low cost. That is an ideal PECD. But in reality, it is not the same. Any modification to this assembly will enhance one and simultaneously it also reduce the other. Suppose if we use an Na2S electrolyte, because we know that QDSE works based with polysulfide electrolyte, this Na2S will give very high power conversion efficiency. But the top electrochromic performers that we have, that is WO3, MO3, or the transition metal oxides, they are unstable in these alkalis. They tend to dissolve very easily. So what happens is these electrochromism, that the color change, is seen for only a very few seconds, and then the counter electrode is pretty much dissolved. Now, if we replace this alkaline electrolyte with a neutral, low-cost electrolyte, that is ferroferry or iron to iron 3, what happens is the solar efficiencies becomes very poor. Though the transition metal oxides are very stable in these low-cost electrolyte, but the electrons that flows through the external circuit that are so less that you see no contrast. You can also have electrochromic conducting polymers P dot that are stable in alkali, that can also give high power conversion efficiency, but they do not yield any good contrast. So we aimed in lab to designing a PCD with a new architecture wherein we used a photoanode, TiO2 series. TiO2 series is extremely robust, easy to process, and has high efficiencies of 6 to 7%. It is also highly scalable. As you can see in the figure, we have gone up to a 5x5 cell. So if you think of taking a design from lab scale to an industrial level, then the first point that comes up is scaling it up. So that's why we use TiO2 series. We have also modified it slightly with a semiconductor polymer P3HT. P3HT is polyhexyl thiophene. This works as an assistant light harvester and also a whole transport material. Now, to achieve a good power conversion efficiency, we have thought of using the same alkaline electrolyte, that is 0.1 molar Na2S solution. And for the electrochromic cathode, we have SiO2WO3Cu. Now, why this? WO3 is a standard electrochrom. You may ask that in the first work in 1996, it was also based on WO3. Why even after a decade, we are still working with WO3? Because it has a very long cycle life. But in this work, we have aimed of achieving a transmittance modulation, which will be more than double than that was achieved then in 1996. It was around more than slightly higher than 20%. So we will definitely try getting more than 40%. For that, what we have done is we have added a thin copper layer below the WO3 layer so that it augments the contrast of WO3 by hot electron. Similarly, on injection. top of WO3, we have added a SiO2 layer, which will restrict the erosion of WO3 film in a basic electrolyte. Now, SiO2 layer as a passivation has been previously used in a lot of other QDSC reports as well. Now, I have assembled my film. I have made a very thin TiO2 over FTO. I have deposited CDS via Sylar on the TiO2 and then drop casted P3HT in chloroform at 80 degrees. Now, why I have this IITH logo throughout is that I want to show that this film never loses its transparency. It is, even if you have a thin P3HT layer, it is still transparent. The thick P3HT didn't work well for us, but I've just shown to show you the color, how it is. Next is the electrochromic cathode. I have electrodeposited a very thin copper layer from a copper salt, washed it, and then again went for electrodeposition of a WO3 layer with a polyperoxotungstenic acid solution, and then annealed it. You can see the color of that. So why electrodeposition? Because in electrodeposition, you can expose the substrate to a very wide region. So you can deposit the material over a long range and at a very high surface area in a very small time. Finally, when you fabricate the PECD, you have TiO2 CDS P3HT, you have 0.1 molar Na2S, and you have SiO2 WO3Cu as your counter. Now, first I have tested for the optical part. Del T at lambda max of the PECD with SiO2 WO3Cu counter electrode is 48.1%, which was much greater than 33.2 with only SiO2 WO3 as counter electrode. I have still kept SiO2 when I'm using pristine WO3. I don't want the WO3 to get dissolved in the alkaline electrolyte. Now, why has the lambda max shifted slightly? When we have only WO3, it was in the range of 465 nanometer, the lambda max. But when you have copper nanoparticles have an absorption peak in the range of 500 to 600 nanometer. So the WO3 and copper has the peak max at around 520 nanometer. So you have a power conversion efficiency of 3.8 and 5.9. 5.9 for these kind of cells is pretty impressive, I feel. Now, you see the lab scale image, what we have got when we have exposed it for 60 seconds under sunlight. We see the dark blue color. The same film, when we have kept it in dark for a couple of minutes, we see the bleaching occurring. So what is the energetics of this PECD? Upon illumination, excited electrons are transferred from CDS and P3HT to the TiO2. Now, electrons reach to the copper through the external circuit, and then they are relayed to the WO3. Hot electrons are produced by copper, are also transferred to WO3. WO3 turns blue. Sulfide reduction occurs and oxidized sulfur regenerates the whole. Now, why hot electrons? Why not SPR? Now, localized plasmon have a tendency to dephase in a femtoseconds time scale. When we have studied the electron transfer kinetics of these kind of cells, we have got it in nanoseconds time scale. So we assume that they are hot electrons. For further checking it, we have run GV with only FTO copper in Na2S solution with a platinum electrode. We see in dark, it's the blue line, and under 0.25 sunlight, you get a significant improvement. Now, had it been only SPR, then under illumination, there wouldn't have been any effect. So the curve would have retraced the dark curve. But when you see certain amount of photocurrent under 0.25 sun, you can say it is a support to hot electrons. These copper films are having nanoparticles of 10 to 25 nanometers. They show a conductance of around 28 microsiemens at room temperature. So in my lab, there has been reports of PECDs which have been fabricated with different transition metal oxides. Now, firstly, we had tried vanadium pentoxide at 475 nanometer wavelength. It gave a del T of 36%. When we made a composite with PDOP, these films gave a transmittance of 65.5%, which was pretty high. The power conversion efficiency of these cells were not very high. It was only 1.4%. We tried improving it in the following year. They used molybdenum oxide. So molybdenum oxide, the del T varied between 24% and 31% over 500 to 840 nanometer. And the power conversion efficiency achieved was 4.59. Now, in one of my previous slides, I have talked about the ways of improving solar energy. One point was carbon material addition. So here I've tried adding graphite nanoplatelets. This gave conductivity of the cell and also escalated the energy charge profile throughout the cell. Now, what are the possibilities for QD-based PCBs? Non-toxic quantum dots capable of delivering high power conversion efficiency. I have used cadmium sulfide, which I can no way call it non-toxic, but you can use quantum dots which are cadmium or lead free, that is copper indium sulfide, copper indium selenide, and still get high power conversion efficiency. There has to be some solution to improve the stability of oxide in basic media. Here I have used one, that is the SiO2 layer. New solid state redox couple electrolytes can also be an alternative to be used. And there has to be approaches to improve the transmission modulation. Now, improving the transmission modulation cannot hamper the high power conversion efficiency. An ideal PCD, we remember, that has to have high power conversion efficiency as well as good optical contrast. So if you see the two photographs that were clicked by me, you can see the color. It is transparent and it also has the IITH building behind it. And when you have a solar connection, you also get efficiency. When you have electrochromic, you can also test single film electrochromic and also a PCD electrochromic, whichever is convenient. So that's all. Thank you. I want to extend thank to Mr. Rishabh Jain and Ms. Anupama Thakur for giving me this opportunity and platform to discuss about my work. I'm open to any kind of suggestions if you have regarding my work. Also, if you have any questions, please ask.
Thank you, Ankita, for a very wonderful talk. Now the session is open for queries. So, Ankita, there are some in the chat box. So, shall I read it for you? Or? Yeah.
Yeah, I'll just try looking at them.
Yeah. So you can start from the bottom.
Also, if a participants can
Anupama, can you
want to
read?
want to ask, you can ask also audible using audio.
Okay, so I'll go up. The first question, I think, what kind of substrate will be used in dye-based PCD solar cell preparation? The substrates are usual. If you're talking about the glass substrate, you can use FTO or ITO as is available. As long as it is conductive on one side, it is fine, and transparent, definitely. What is FTO? It is similar to ITO. Yes, it is similar to ITO. I think there is already a lot of answers to that.
Okay.
Yeah,
there was one question before asked by Chavi. Quantum dot deposition among all mentioned, which technique is better for the quantum dot deposition?
Okay, it might be in the top.
Yeah, it's on the top.
Can you just tell me the time? What time?
519.
Oh, yes. Yes, sir, got it. Okay. Now, as I have shown that quantum dots, can you see the slides?
Yes, it's visible.
Okay. 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 So in my lab, I prefer in situ techniques like SILAR or CBD. Why so? Because I feel there is more uniform deposition over the TiO2 film. But I will accept it that in some case, when you have an in situ growth of quantum dots, you may have in some places quantum dots that have moved to nanometer scale. Like quantum dots has to be restricted below 10 nanometer. You have certain agglomeration and it tends to grow 20 to 30 nanometers. So you then may not call it as a quantum dot. But you can also use linkers and stuff to regulate the check. Some labs prefer ex situ techniques because I have talked in my previous slide why size control is such an important factor in quantum dot sensitized solar cells, because it will give a, it will check on the emitted light. So some labs prefer preparing the quantum dots previously from hot injection method or hydrothermal method and then depositing it. But like if you want to make a hot injection quantum dot, you have to have real like setups in lab, like Schlenk lines and proper inert atmosphere, glove box. So if you have these techniques, please go ahead with an XC2 method, or you can also compare the two. I hope I have tried to answer your question to the best of my abilities.
Hello,
Yes,
Ankita
Ankita.
ma'am. Thank you for the wonderful session. I would like to ask a question. As you have explained that QD deposition methods. Hello?
Yeah, I'm listening.
Yeah. Okay. Ma'am, I just wanted to know if you are telling that in situ method are better than ex situ methods, then basically what you are doing, growing that QDs, what is that SILAR method actually? Can you please explain it in a brief?
Sure. I have not gone into much details in this. Do you see the photograph that I have attached? It is of this paper. I've taken it from this paper. You have two precursor solutions. You have a cadmium sulfide, maybe I'm talking about CDS. You have a CD2 plus precursor solution. You may take cadmium nitrate, cadmium acetate, and you have a sulfide precursor solution, Na2S maybe. So what you do is you have the TiO2 film that is coated on FTO. You dip it in the cadmium sulfide cadmium solution. You take it out, you rinse the excess out of it, and then you dip it in the sulfide solution. So you have CD2 plus ions, which adheres to the TiO2. And then when you dip it inside the sulfide, you form the CDS. So this is what I mean by in situ growing.
Ma'am, then what is the difference between this dip coating and this your CBD method? What is the difference between the two?
Okay, this is precursor solution. They are all pretty much of the same kind. In CBD solution, CBD method, what you have the precursor solutions together. You stir it at a particular temperature. You keep your films immersed for a really long time, and the reaction keeps happening inside the beaker where you have your films. So there also you will see after a certain point of time, you have the quantum dots growing on it. Suppose I'll tell you an example. You have indium acetate. Suppose if you take indium acetate in a beaker, you take a sulfur precursor, maybe any kind of sulfur precursor, you put it, and maybe thioacetamide, you put it inside the beaker. You add water, you put it in a 70-degree temperature over a stirrer. You keep your films immersed in the beaker. Now, as the reaction goes on for maybe 1 hour, 2 hours, you see the indium sulfide forming over the TiO2. So that is how you can also, it is not that you have to follow a indium sulfide can also be grown by SILAR method, but you have proper size control maybe in CBD, or there are literatures where they have compared when you have suppose CDS can be grown by chemical bath deposition, CDS can be grown by SILAR, CDS can be made by hot electron injection method and then deposited. Each method has its own advantages, has its own size control, dimension control. So depending on your requirement, you can use. I use SILAR in my lab. I find it user-friendly because it is just dipping into precursor solution. You can see the film forming right in front of you. So it is easier.
Ma'am, how you are controlling its size? That because quantum dots are too much sensitive about the size of the CBD.
Yes. Now, that's I said that in situ method, you sometimes lose out on the size control. So for what we do is we monitor the dip time. We monitor the concentration of the solution, how long we are dipping it, how fast we are withdrawing it from the solution. These kind of things control the size. There are something called a withdrawal time. That is how fast you withdraw the film from the solution, how long you keep it immersed. So these kind of things affect the size.
One more question I would like to ask.
Yes, sure.
In the ex-situ methods, using that thermal method, then how will we be able to control the size? Yes, ma'am.
That is also like you have to take a particular hydrothermal method is like when you put it in a certain amount of pressure and temperature. So when you regulate the pressure and temperature appropriately in a hydrothermal synthesis, you get very fine morphological structures. You get wires of particular dimensions, particular size. You can definitely control. If you read a few literature on hydrothermal paper, I can assure you,
I'm
you will see
already
how
working.
lovely they are.
I'm sorry to interrupt, but I am already
Yeah, sure.
working in this hydrothermal method, but I'm
Okay.
not being able to control its size because I don't know how to control its pressure. Temperature is being controlled, but I don't know how to control its pressure.
No,
Could
if
you
you
please help
control
me?
the temperature, okay, if you control the temperature, at the same time, the pressure built inside the autoclave gets monitored because you cannot change. I don't know if you are using an oven or if you are using a microwave reactor.
I'm using the oven.
Oven, okay. Hydrothermal methods are better if you use a microwave reactor. In an oven also, if you tighten the autoclave properly, you increase. Why don't I can just suggest you, I don't know how much it will be helpful. I have tried it. That is, if you put a reaction in, suppose you have glucose and you put the reaction, you take out materials after 1 hour, 2 hours, 3 hours and check. I have done that and I have seen the size difference. Dimension, morphology, everything grows in a different way when you have temperature fluctuations.
Okay,
If you want, I can share a couple of papers with you if you want. I have it. I have tried it. But I don't know if it
that
will
will
be
be
helpful
really
in your
helpful,
field of
ma'am.
work.
Kindly share me your ID, please, in the chat box so that I can contact you after this session also for
Sure,
the
sure,
help
sure.
and the assistance. That will be really
Sure,
helpful. And
sure.
one question I would also ask,
Yes.
what is the dimension of this FTO you are using as a substrate?
Are you asking about only the FTO or the active area of the
What are the
TiO2?
dimension of the FTO you are using as a
Okay.
substrate?
The FTO I have used maybe around.
No, I'm asking only for the.
Huh? Can you repeat the question once again?
I'm asking about the dimensions you have used FTO as a substrate.
I have used 2 centimeter into 2 centimeter FTO, but my active area means the TiO2 covered area, that is 0.1 into 1.15. It's that area. The active area of the TiO2 is very small. FTO is very big.
Okay.
Am I able to make? Wait, I'll just show you.
Thank you so much, ma'am. Thank you. Please kindly
See, the
share your email ID so that we can contact you afterwards too.
sure.
Yeah,
If you
Chavi,
see if
I'll share. Yeah, Chavi ma'am, I'll share you the email ID. Yeah,
Thank you
I'll
so much,
connect you
ma'am.
to Ankita.
Thank you. Thank
okay,
you.
thank you so
Thank you,
much.
Anu. Thank you.
Okay,
So
Ankita, we can take
should
up
I go
another
on to the
question.
next? Yes. What is the
Yeah, yeah.
transmittance of light by using?
Ankita, I have one connected question to the previous question.
Yes, yes. Sure.
Yeah. Actually, I want to ask that in the Ciliar method, how are you confirming that your that SC or selenide or sulfide species is binding to the cadmium or the TiO2 layer?
No, it cannot bind to the TiO2 layer because we have first coated it with CD2 plus. So there are CD2 plus everywhere over the TiO2.
So how
When I
you are
dip it,
confirming the uniformity of the CD2 plus? That it is
how I'm
actually
confirming,
that it is actually binded over to the whole active area.
I'm not very clear, but I just can show you this. Suppose if you have a TiO2, it is this color. Suppose it's white color.
Transparent. Yeah, white.
Transparent. It is generally not transparent. I have made for transparent. It's a white color film. Now,
Okay.
when you start
Yeah.
growing CDS, you can see the color changing to pale yellow and then deep yellow. You can, and then definitely there are characterizations we go for, that is XRD, SEM, TEM, to check on the sizes and if how much CDS layer thickness. We go for cross-sectional SEM images to check on the thickness of the TiO2 layer and then the CDS layer on top of that.
So, did you go for these characterization techniques?
Yes, yes, yes.
So, what are the size of the formation of the CDSC or CDS quantum dots onto the? layer?
You are asking for the particular CDS?
Yeah,
CDS is a range
particularly
of
using the
around.
Silar method.
Okay, Salar method, the size is sometimes around 10 to 20 nanometer because Salar sometimes tends to grow on top of the other one. So I cannot say it is absolutely below 10 as it should be for the case of quantum dots. It's around 10 to 20. But if you say about the TiO2 CDS layer thickness, then it is in the range of 10 micrometer thickness. Like if you see cross-sectional SEM images, the
Do
entire
we
thickness is around.
So do we actually call them layers or maybe films or the quantum dots?
There are pores. These TiO2 are mesoporous. So these quantum dots grow inside
Okay.
those pores. You can see the color of this quantum dot not only from the top, even from the back of the TiO2 film, the yellow color.
Okay.
So you can see that it has percolated through.
Okay, I'm embedded into it. Okay.
Embedded into it, yes.
Yeah. Okay, thank you.
So someone is most welcome. Someone is asking, I'm interested to know how to manage the challenges in coating with Sila technique. I think I've just answered it. So adding to the question, I'm not sure what is BBAR. Are you asking about the anti-reflective coating that is used?
Yeah, Praveen sir, you can unmute yourself and directly ask. BBR. Yeah. Meanwhile, yeah, Praveen sir. Yeah. Praveen sir, you have to unmute yourself.
I think he's talking about the anti-reflective coating.
Actually, we have used commercial FTO, so I am not sure whether, I'm not clear about the question also, whether the transmittance will hamper or not. Whatever commercial FTO we have used, before coating the material, we have gone for delta T transmittance measurement, and we have got it close to 95 to 100%. And if we have not, then we'll set the what you call baseline to that level, so that after that, when we do, the transmittance of FTO is not hampered with the film. Am I clear, sir? Is there anything else that you were intending to ask? Maybe not clear to me.
Dr. Praveen, you are or not audible? Yeah, he's saying, okay.
Okay, so
you can go to the next question.
Jaspreet has asked me, is there any losses in quantum dot solar cells? I mean, recombination thermal losses. Of course, I have talked about there are multiple recombination pathways in the film at different interfaces. So there are quite a few amount of losses. That's why we don't reach the Shockley-Queisser limit. Yes, we can also use quantum dots of silicon and germanium, but I have never used it, so I'm not very thorough with it. But there are reports where they have used silicon quantum dots. And I think preparation of silicon quantum dots is quite a challenge.
Yes.
You have mentioned quantum dot PCD, they are commercially available. No, I don't think they are till now commercially available. But PCDs are there, but quantum dot PCDs research is still ongoing. So hopefully it will be commercially available sometime in the future. QDSCs itself is not till now commercially available. If the QDSC PCD are commercially available, they are cost effective. Also, which industry is going to use them for PV panels currently? I don't think till now any industry will use them in PV panels because they are not established yet as in the industry level. Lab scale, multiple researches are going on, and somewhere perovskite solar cell has taken over quantum dots. So quantum dots have fall behind, but we are trying to work on this forum because PCDs will eventually find this, quantum dot based PCDs will eventually find this application. But for that, there are certain challenges, as I've shown you. There are not one or two, there are multiple challenges that needs to be overcome before we go for commercialization. What about the adhesion of the film coated by the author in the research work of FTO and ITO substrate? What is intended by adhesion? Like when I grow a film, when I'm coating it by doctor blading and then annealing it, the film pretty much sticks to the FTO surface, because if FTO on one side is like fluorine doped tin oxide, so it is a rough surface. So is it what?
Yes, it's
I
correct.
think.
But what
Okay.
about the adhesion of the coated film by the author? Whether it is peeled out easily or it can be adhered in a proper manner?
No, it is not peeled out, sir. It is in sticking to it till the last, because after sometimes we have like disassemble the cell and then again went for few other characterizations. Sometimes when reviewers ask, so it has not peeled and it is pretty stable over a couple of hours.
Does any kind of mechanical analysis or mechanical stability things you have done like under the characterization tool?
Mechanical stability analysis, meaning are you talking about stability under sunlight for a really long time?
Like on load, some kind of load you are giving some kind of testing like tape
No,
test or
we
adhesion.
haven't done any kind of mechanical stability that way, because we have tried very hard to keep the WO3 film with the SiO2 coating intact on the counter electrode side. We were pretty
Okay.
worried that because in all previous reports, never they have used an alkaline electrolyte for WO3. We wanted to
Okay.
try it with SiO2 and it was working well, but it was not uh, there for like multiple cycles. We didn't go on for proper cyclings. We tried
And
around 10 to 15, 20 cycles and then we had to stop.
okay, regarding my earlier question on the BBAR, it's a broadband
Yes,
anti-reflection
yes.
coating only. So
Yes, sir.
does any kind of multi-layer coating have you developed on the FTO substrate to improve the transmission or to make the more amount of light should be go inside of the solar cell?
No,
Does any
sir.
kind of this?
We have Tech 8 and Tech 15 FTOs in lab. Commercially, we have purchased it and we have used that only and started directly using that, just washed the FTO in the regular process under ozone layer and all, and then went for it. We didn't go for any anti-reflective coating over it.
Okay, thanks. Okay.
Thank you, sir. Okay, someone has asked me, Abhishek, can I use photoelectrochromic materials in 3D printing technology? I'm really sorry, I don't know if you can use photoelectrochromic materials in 3D printing technology. You can try, but I am not sure if you can use it. I don't want to give wrong information and waste your research time. Even number of cycles do matter. Yes, of course, if you're talking about Sylar, then number of cycles do matter, that how many Sylars you are using. In my case, I have used 6 Sylar cycles. The number of cycles do matter. What is the role of PC material in printed electronics? 3D printing, printed electronics. I apologize, I'm not very sure about this. In Sylar, I guess I don't get this question. Is it a question at all? How we can improve solar energy conversion by FRET? How we select FRET pair? Okay, so FRET, what we can do is we can have, as we know that in FRET we can have two materials which has their absorption and emission band overlapping. So I have just tried my hand on using, not exactly me, one of my seniors have done in lab. I've just been lucky to see that is he has used CDS with PCDTBT, and this polymer and the quantum dots had their absorption and emission band lying one over the other, so it showed really good FRET emission. How we select the FRET, I think by absorption. If you run absorption spectrum of individual and if you see there is an overlap, distinct overlap, and then you can, I think, identify that these two quantum dots or this polymer or these material can work as FRET or not, this particular pair. Thank you so much for study. How to study growth mechanism of the synthesized material. Which material you're talking about? About Mr. Kishore? About Mr.
Ankita,
Okay,
you have missed one question. Yeah.
Okay, just which question, Anupama? Can you just repeat once? Oh, is the
From
effect of
Girish.
pressure on
Yeah.
effect of pressure on morphology during synthesis?
Yes.
Okay, so as I said, in hydrothermal synthesis are generally temperature and pressure modified. So exactly how pressure affects, I won't be able to tell you, but basically when we have it in different temperature and pressure control, the morphology during synthesis changes. Like I have seen when we have it with a surfactant and we apply a certain amount of pressure, any oxide has a tendency to grow into sheets. When we don't have the surfactant and we use the same amount of temperature and pressure, it has a tendency to roll up and grow into a wire. But exactly how like pressure dominates in these kind of synthesis, I'm not very sure about it. Like we use a sealed pressure vessel, and the type of the reactions that we carry on both has high temperature and pressure. And there is also, like hydrothermal includes techniques of crystallization as well, with the range of pressure and temperature that we use. But effect on pressure and morphology, I cannot tell you that this to this range of pressure will give you this kind of morphology. I'm not sure. So Anupama, will I go to the next one? How to calculate energy? Yeah. Okay. How to calculate energy band gap by PL or XPS? Sir, I have not calculated energy band gap by PL or XPS. What I have done is either we can run CV and we get a redox and redox peak, oxidation peak and a reduction peak. From there, I can calculate the energy levels and then subtract it to get the band gap. Or I can take the band edge from the absorption profile. I think that is what mostly is done. That is when you take an absorption profile from the band edge, you can take the nanometer and then 1240 divided by the wavelength, you get the band gap. That is what is usually done. Is there any application in printing technology? I'm sorry, but I'll definitely look at it today. There's so many questions on printing technology. Are the cost effective? What about PCDs? Are they cost effective over silicon used photovoltaic cells? Of course, they are cost effective. The QDSCs, PCD based QDSCs, they are really cost effective, but they have certain challenges, as I've said, that the crystalline silicon solar cells or in silicon, they have high carrier mobilities, high efficiency. In spite of being expensive, this is commercialized because of its advantages. Several these DSSCs, QDSCs, in spite of several lab scale research, it has not been till now commercialized because it has many drawbacks. So they are cost effective, but they are still not in a stage to be commercialized or even taken to industrial level maybe. I'm in my lab is trying to scale up step by step. As I had shown, I have moved from 1 centimeter to 5 centimeter. I'm going step by step, but I have not reached that level. I think I have shown you here that I'm going up step by step. I'm working on cooling techniques on PV panels using these PCs, which will be commercially available afterwards. What about their heating range? Energy efficiency output. What kind of heating range you're talking about, Aryan? What is this? I'll go on to the next one if he just clarifies the question. What is the size of the mesoporous TiO2? They are 25 nanometer range. The mesoporous TiO2 are 25 nanometer range particles. What is the size of the quantum dots? Ideally, it should be 2 to 10 nanometers, but when you have it in situ technique growth, it may slightly go beyond 10. Among all techniques, which one technique we are obtaining better hysteresis loop? I'm not sure which technique you're talking about, techniques and hysteresis loop. If they're showing enhanced magnetic properties, I haven't checked magnetic properties, I'm sorry. If somebody has already clarified, band gap usually not calculated by PL data. Normally use UV and XPS, yes. I think I have reached last, Anupama. I have just missed on Aryan's question.
Yes, ma'am, are on this side.
Yes, yes.
Yes, good evening, ma'am. So, ma'am, currently I am working on the cooling techniques of PV panel. What I have seen is that. Am I audible?
Please, one at a time. Please, one at a time.
So ideally considering no loss.
I'm not sure what's going on.
Within the specifications, within the
Okay, Aaron, first you speak. Then Madhu.
Yes. Am I audible?
Yes, you are audible.
Yes, you are audible, please.
So my question is like I'm working on the cooling techniques of PV panel. Since nowadays the silicon-based cooling panels are used, in which due to the heating effect, the efficiency is means lost to a great extent. So,
Yes.
Heating effects affect the electrical efficiency a lot. So,
Yes.
what about these PCEDs that you are using in your labs? Have you worked on the heating effect of those? Like, to what extent their electrical
not
efficiency
really.
is being affected?
Not really, because we are basically trying to work on the materials in designing a PECD, because designing a PECD, overcoming the challenges, is itself a very difficult job. So we are trying to take optimum materials which will work both as PECDs and give good electrochromic contrast and as well as efficiency. So I have not looked into the heating aspect of it. We're just working on materials that will work as PECDs.
Okay, ma'am, and ma'am, one more query. Since we have
Yeah.
already answered that they are really cost effective, can you give an estimated idea like what cost extent they are being cheaper from the silicon available panel?
No, sir. If you want in a lab scale, I can tell you how much Sigma Aldrich is taking for these materials, but I don't know at industrial scale what is the cost difference.
Okay, no issues. Okay, ma'am, thank you so much.
Thank you. I'm sorry if I have not been able to answer you properly.
No issues at all. Thank you.
Someone else
any
was
more?
also trying to.
I think Madhu, you can take the query now, Mr. Madhu. You were speaking earlier. Okay, I think. Any more queries? Anupma?
Okay, so we can end up the session. So thank you, Ankita, for a really very informative talk and very interactive session with our participants. Like you took up so many queries. So now before we end up, I would like to request everyone to kindly turn on your camera and we can make it memorable for our speaker. So we can have a group photograph. Yeah, Ankita, you can stop sharing your screen.
Am I visible?
Yeah. So I request everyone whosoever. No, not yet. You can close it. Stop sharing.
Yeah. I think now I'm visible.
Yeah. I request everyone.
Thank you, Ankita. It was a great session.
Thank you so much for giving me this opportunity.
Yeah.
Ankita, I think your video is on.
It's been our pleasure.
Yeah, it's our pleasure to have you.
Is the video fine?
Yeah, so it's still not visible. Wait, maybe some network issue. It will come again.
Yeah.
Anyone else who would like to join us? can turn on your camera.